Hello everyone, welcome to Compiler Design video series. In our previous video, I have already discussed about code optimization, unit number 7. Explain code optimization techniques. There are different code optimization techniques like compile time evaluation, common sub-expression elimination, variable propagation, code movement, strength reduction and dead code elimination, peephole optimization. Characteristic of peephole optimization: there are redundant instruction elimination, unreachable code, flow of control optimization, algebraic simplification, reduction in strength and machine idioms. Then after discuss about data flow analysis, properties of data flow analysis. There are definition point, reference point, evaluation point and different properties like available expression, reaching definition, live variable and busy expression. So all these topics are already discussed in our previous video. In today's video, I will discuss about unit number 8, code generation. In this video, I will discuss about different topics like role of code generator, issues in the design of code generation, target machine and instruction set, basic blocks, next use instruction, register and address descriptors, DAG representation of basic blocks, generating code from DAGS, etc. Then first is role of code generator. What is the role of code generator? Code generator is the final phase of compilation process. It takes an intermediate representation of the source program as input and produces an equivalent target program as output. Here position of code generator in compilation process is shown. Your source program is passed to the front end of compiler which generates intermediate code. It passes to code optimizer. Then it passes the intermediate code to code generator and code generator produces the target program. So your target code should have different properties like correctness, efficient use of resources of target code, quick code generation and high quality. So issues in the design of code generation. There are total 7 issues. First is input to the code generator. Second is target program. Third, memory management. Fourth, instruction selection. Fifth, register allocation. Sixth, choice of evaluation. Seventh, approaches to code generation. Then what is doing in the input to the code generator? Input to the code generator consists of the intermediate representation of the source code. There are several types for intermediate languages such as postfix notation, syntax tree, quadruples, DAGS, etc. So the detection of semantic error should be done before submitting the input to the code generator. The code generation phase requires complete error-free intermediate code as an input. Second is target program. The output of the code generator is the target program. The output may take on a variety of forms. It's an absolute machine language, relocatable machine language, or assembly language. Producing an absolute machine language program as output has the advantage that it can be placed in a location in memory and immediately executed. So producing a relocatable machine language program as output is that the subroutine can be compiled separately. So a set of relocatable object modules can be linked together and loaded for executing file by a linking loader. So producing an assembly language program as output makes the process of code generation somewhat easier. Third is memory management. So mapping names in the source program to address of data objects in runtime memory is done cooperatively by the front end and the code generator. We assume that name in a 3-address statement refers to a symbol table entry for the same. From the symbol table information, a relative address can be determined for the name in a data area. Fourth one is instruction selection. If we don't care about the efficiency of the target program, instruction selection is straightforward. It requires special handling. For example, any sequence of statements like A is equal to B plus C and D is equal to A plus B would be translated into machine code like move B, R0. First move any operand in register, then add C, R0. Then move R0, A, move A, R0, add E, R0, and finally your answer is store in D. So move R0, D. So your statement like move R0, A, then move A, R0, which is redundant. So we can eliminate that statement. Fifth one is register allocation. If the instruction contains register operands, then such a use becomes shorter and faster than that of using in memory. So the use of registers is subdivided into two subproblems. During a register allocation, we select the set of variables that will reside in registers at a point in the program, and during a subsequent register assignment phase, we pick the specific register that a variable will reside in. So finding an optimal assignment of registers to variable is difficult. Mathematically, that problem is NP complete. So next is choice of evaluation. The order in which computations are performed can affect the efficiency of the target code. So some computation orders require fewer registers to hold intermediate results than others. Picking a best order is another difficult NP complete problem. And seventh is approaches to code generation. The most important criteria for a code generator is that it produces correct code. So correctness takes an special significance because of the number of special cases that code generator must face. Given the premium on correctness, designing a code generator so it can be easily implemented, tested and maintained is an important design goal. So these are the 7 issues in the design of code generation. It is a very important topic, many times asked in your GTU exam, like list out issues in the design of code generation and explain, or list out the issues in the design of code generation and explain any 4. Next is the target machine and instruction cost. Target machine and its instruction set is a prerequisite for designing a good code generator. So we will assume our target computer models a 3-address machine with load and store operation, computation operation, jump operations and conditional jumps. So the underlying computer is a byte addressable machine with n general purpose registers, which are R0, R1, R2 up to Rn. The 2-address instruction of the form operator source, destination. It has following opcodes like for move, MOV source to destination, for addition, ADD source to destination, and for subtraction it's SUB, then source to destination. So the address modes together with the assembly language forms and associated cost as follows. Like your mod is absolute from M to address M, then its cost is 1. From register to register, R to R, then cost is 0. If any index is specified, then K of R address is K plus content of R, which required extra cost 1. In indirect register, it's a pointer R, address is contents of R, extra cost is 0. In indirect index, pointer K of R, contents of K plus contents of R, which required extra cost. For example, instruction set, the instruction cost can be computed as 1 plus cost associated with the source and destination addressing modes given by the extra cost. For example, calculate cost for move B, R0, add C, R0, move R0, A. So instruction cost for move B, R0, it's a absolute mode, then value extra cost is 1. Then it store from any content it required 1, and for any register it requires 2. So 1 plus 1 plus 0 is equal to 2. Same for add, it's a 1 plus 1 plus 0, 2, and move R0, A, for move value is 1, for register value is 0, and for A extra cost will be 1. So 1 plus 0 plus 1 is equal to 2. So the total cost will be 2 plus 2, 4 plus 2, which is 6. So total cost is 6. Next is basic blocks. A basic block is a sequence of consecutive statements in which flow of control enters at the beginning and leaves at the end without halt or possibility of branching except at the end. So the following sequence of 3 address statements forms a basic block, like T1 is equal to A into A, T2 is equal to A into B, T3 equal to 2 into T2, T4 is equal to T1 plus T3, T5 is equal to B into B, and T6 equal to T4 plus T5. So some terminology used in basic blocks, like a 3 address statement x is equal to y plus z is said to be define x and use y or z. A name in a basic block is said to be live at a given point if its value is used after that point in the program or maybe in another basic block. So algorithm for partition into basic blocks: input is a sequence of 3 address statements and output will be list of basic blocks with each 3 address statement in exactly one block. So there are two methods. First, we determine the set of ladders. For that, we use the following rules. The first statement is a ladder. It means we initialize some value in the variable. Any statement that is the target of a conditional or unconditional goto is a ladder, and any statement that immediately follows a goto or conditional goto statement is a ladder. And second is, for each ladder, its basic block consists of the ladder and all statements up to but not including the next ladder or the end of program. For example, program to compute dot product. Product is equal to 0 and I is equal to 1. Just start with begin initialization of product and I, then do while loop. So just write do, then product is equal to product plus A of T1 into B of T2 and I is equal to I plus 1 while I less than or equal to 20. Then after end. So where your value of I is less than or equal to 20, at that time this do while is repeated. So the 3 address code for this program: first, product is equal to 0, I is equal to 1, then temporary T1 is equal to 4 into I, T2 is equal to A of T1, T3 is equal to 4 into I, T4 is equal to B of T3, T5 is equal to T2 into T4. Then T6 equal to product plus T5. Then product is equal to T6. T7 is equal to I plus 1. I is equal to T7. If I less than or equal to 20, then go to T1 statement, which is your step number 3. Then go to 3. So let us apply an algorithm to 3 address code to determine the basic blocks. Statement 1 is a ladder by rule 1 and statement 3 is a ladder by rule 2, since the last statement can jump to it. Therefore, statement 1 and 2 from a basic block and the remainder of the program beginning with statement 3 forms a second basic block. These two initialization from basic block 1 and these all procedures are from basic block 2. Next is use information. The next use information is a collection of all the names that are useful for next subsequent statement in a block. So the use of a name is defined as follows. For example, consider a statement x is equal to I and j equal to x operator y. That means statement j uses value of x. So the next use information can be collected by making the backward scan of the programming code in that specific block. And second one is storage for temporary names. For the distinct names, each time a temporary is needed and each time a space gets allocated for each temporary. To have optimization in the process of code generation, we pack two temporaries into the same location if they are not live simultaneously. Consider the following three address code, which is T1 is equal to A into A, T2 is equal to A into B, T3 equal to 4 into T2, T4 equal to T1 plus T3, T5 is equal to B into B, and T6 is equal to T4 plus T5. These 6 temporaries are removed by these two temporaries, like first use T1 is equal to A into A and T2 equal to A into B. In future you will not use T2. So now you can reuse the variable T2. So 4 into T2. Here T2 is multiplication of A and B. Store in again T2 because later on that values are never used. Then after T1 plus T3. Here value of T3 is stored in here T2. So T1 plus T2, which is stored in again variable T1. So the value of T1 is overwrite by addition of T1 and T2 because later on that A into A value is never used. Here B into B is stored in another variable T2. Now 4 into T2 is overwrite by B into B. Then after add value of T1 and value of T2 and your final result is stored in T1. So here only two temporary variables are used. Next is register and address descriptors. The code generator algorithm uses descriptors to keep track of register contents and address for names. In address descriptor, it stores the location where the current value of the name can be found at runtime, and the information about location can be stored in the symbol table and is used to access the variables. In register descriptor is used to keep track of what is currently in each register, and the register descriptor shows that initially all the registers are empty. As the generation for the block progresses, the registers will hold the value of computation. Next, register allocation and assignment. So efficient utilization of register is important in generating good code. So there are 4 strategies for deciding what values in a program should reside in a registers and which register each have should reside. First one is global register allocation. There are 4 strategies: global register allocation, usage count, register assignment for outer loop, and register allocation for graph coloring. In global register allocation, it is adopted while doing the global register allocation. The global register allocation has a strategy of storing the most frequently used variables in a fixed register throughout the loop. Another strategy is to assign some fixed number of global registers to hold the most active values in each inner loop. The registers are not already allocated may be used to hold values local to one block. Like in C language, do the register allocation by using register declaration to keep certain values in register for the duration of the procedure. Second is usage count. It is the count for the use of some variable x in some register used in any basic blocks. So the usage count gives the idea about how many units of cost can be saved by selecting specific variable for global register allocation. Next one is register assignment for outer loop. For example, consider there are 2 loops, L1 and L2. L1 is your outer loop and L2 is an inner loop. Allocation of variable A is to be done to some register. So if allocation in loop L2, then it should not be allocated in L1 minus L2. If A is allocated in L1 and it is not allocated in L2, then store a on entrance to L2 and load while leaving L2. If A is allocated in L2 and not in L1, then load on entrance of L2 and store on exit from L2. Fourth one is register allocation for graph coloring. The graph coloring works in 2 passes. Working like in the first pass, the specific machine instruction is selected for register allocation. For each variable, a symbolic register is allocated. In the second pass, the register inference graph is prepared. In register inference graph, each node is symbolic registers and an edge connects to nodes where one is live at a point where other is defined. Then a graph coloring technique is applied for this register inference graph using K color. The K colors can be assumed to be number of assignable registers. In graph coloring technique, no 2 adjacent nodes can have same color. So in register inference graph, using such graph coloring principle, each node is assigned the symbolic registers so that no 2 symbolic registers can interfere with each other with assigned physical registers. Next, DAG representation of basic blocks. The directed acyclic graph, which is DAG, is used to apply transformations on the basic blocks. A DAG gives a picture of how the value computed by each statement in a basic block used in a subsequent statements of the block To apply the transformations on basic block, a DAG is constructed from 3 address statement. This DAG representation, which are already discussed in unit number 5. So a DAG can be constructed for following type of labels on nodes. First is, leaf nodes are labeled by identifiers or variable names or constants. Generally, leaves represent R values. Interior nodes store operator values. And third is, nodes are also optionally given a sequence of identifiers for label. So the DAG and flow graphs are two different pictorial representations. Each node of the flow graph can be represented by DAG because each node of the flow graph is a basic blocks. For example, if you have to calculate summation of 10 different values, then first initialize 0 into variable sum. So sum is equal to 0. Then in a for loop, for I equal to 0, I less than 10, I plus plus, then sum equal to sum plus a of t1. So the 3 address code for this code is sum is equal to 0 and I is equal to 0. This 2 initialization goes into block B1. Then rest of process goes into block B2. So the application of DAGs are, it's used in determining the common sub-expression, determining which names are used inside the block and computed outside the block, simplifying the list of quadruples by eliminating the common sub-expression and not performing the assignment of the form x is equal to y unless and until it is a must, determining which statements of the block could have their computed value outside the block. Next is generating code from DAG. There are 3 different methods for generating code from DAG directed acyclic graph. First one is rearranging order, second one is heuristic ordering, and third one is labeling algorithm. In rearranging order, the order of 3 address code affects the cost of the object code being generated, in the sense that by changing the order in which computations are done, we can obtain the object code with minimum cost. For example, T1 is equal to A plus B, T2 is equal to C plus D, T3 is equal to E minus T2, and T4 is equal to T1 minus T3. So the code can be generated by translating the 3 address code line by line. First move value of A into R0. So move A comma R0. Add B comma R0. Move C comma R1. Add D comma R1. Move R0 comma T1 and move E comma R0. Subtract R1 comma R0. Move T1 comma R1. Sub R0 comma R1 and move R1 comma T4. Now if we can change the order of line, like first write T2 is equal to C plus D, then T3 equal to E minus T2, then T1 is equal to A plus B, then T4 is equal to T1 minus T3. Then your improved code will be move C comma R0, add D comma R0, move E comma R1, sub R0 comma R1, move A comma R0, add B comma R0, sub R1 comma R0 and move R0 comma T4. In heuristic ordering, there are considered interior nodes. While unlisted interior nodes remain present, then pick up unlisted node N whose parents have been listed, while the leftmost child of N has no unlisted parent and is not a leaf, then list M and N is equal to M. So it considers numbering. First generates the DAG representation for given graph, then consider the numbering from top to bottom and from left to right, then perform the computations. In a labeling algorithm, it generates the optimal code for the given expression in which minimum registers are required. Using labeling algorithm, it can be done to tree by visiting nodes in bottom-up order. By this, all the child nodes will be labeled by its parents node. So, in code generation, I will discuss about role of code generator, issues in the design of code generator. These all types of questions are asked in your GTU exam. The target machine and instruction code, basic blocks, next use information, register and address descriptors, register, allocation and assignment, DAG representation of basic blocks and generating code from DAGs. Thank you.